two divisions of meiosis, anatomy of the male, and spermatogenesis, anatomy of the female, and oogenesis. And so spermatogenesis is the generation of sperm, oogenesis is the generation of oocytes, also known as the egg, but I want you to know it as the oocytes, noting when development is arrested. This will make something very different with a female versus a male. Like with this one, again, we start off with 1 and we get 4. With this, we get 1 and we get 1 out of that, if we even get to that point. How many divisions are in meiosis? There are a total of 2. This is going to complete both of those divisions. This one, not necessarily. So there's the difference. 3 phases of the ovarian cycle, 3 phases of the uterine cycle. So we're going to watch what's going on in the ovarian cycle. It's going to be very cyclic, right? Okay. It's going to be in sync with what's going on in the uterus. And the events of the ovarian cycle and the uterine cycle together, that's what we're going to call, folks, the menstrual cycle, as a combination of both of them. So we have to keep in track of what's going on in the ovary and what is happening in the uterus. So, gametogenesis. I kind of explained this already, why we need to perform meiosis. We need to perform meiosis in order to get our gametes, also known as the germ cells. And those are the only cells in our body that are going to undergo meiosis in addition to mitosis. All right? Let's identify the terms haploid versus diploid. This one I want you to recognize because this could show up on your final. Understanding what haploid versus diploid is. A diploid cell has 2 copies of the chromosomes. Diploid. A haploid cell has only 1 copy. So when you perform mitosis, you start off as being diploid and you end up as being diploid. In mitosis, you preserve what we call the ploidy. That's what we call the ploidy, the how many copies of chromosomes that you have. That's the ploidy. In meiosis, you started out as diploid, and then you end up as being haploid. In fact, after the first division in meiosis, you already become haploid. So that's the difference. 1 copy, 2 copies. Okay, mitosis, diploid to diploid, meiosis, diploid to haploid because it divides twice. So that at fertilization, you have a haploid and another haploid, they can unite, and then you go back to diploid. And when they develop into an embryo, then it's just several rounds of mitosis all over again. Okay, so let's look at this. I don't want you to memorize every single step. Remember, there's no essay that is in here, but I just want you to get the general understanding of what's going on. What you know about PMAT, right? Prophase, metaphase, anaphase, telophase, there's going to end up being a PMAT1 and a PMAT2. That's what goes on in meiosis. So let's look at what's happening here, okay? We go from 2N to already 1N. The way that some textbooks will mention it, we go from 1N to 0.5N technically, but for our purposes, I want you to know that we go from diploid to haploid already in the first division. So this is what I want you to, rather than drawing it out, I want you to kind of understand what is the big picture here, okay? Whatever is in the green and whatever is in the purple, the green and the purple represent, okay, 1 set from your mom, 1 set from your dad, okay? So take a look at what happens here, all right? These are completely different chromosomes. And then you have 2 pairs of 2. And then you have them kind of line up first. And so this is another thing that's very different in mitosis versus meiosis. In mitosis, whatever daughter cells you get out of that division is identical to the parent that it came from. Identical. However, in meiosis, we have something called genetic recombination. So there's a difference that is in there, okay? So let's just say this first green one was chromosome number 1. This second green one was chromosome number 2. And this was the set that came from your mom. This is chromosome number 1, chromosome number 2. This is the set that came from your dad. Look what happens, Okay, not so much with this one, but look at what happens when these two line up. What happens? There is a switching that is in there. That's recombination. That is recombination. Okay, and then now they are going to split. You don't need to know the term tetrad or dyad, but, okay, what do we notice now? We have cut it, but, oh look, there's a purple in there, there's a little green that is in there. There was a recombination. Does this still have chromosome 1 and 2? Absolutely. And so does this. Only this time, instead of having 2 pairs, we only have 1 pair. Not 1 pair, but instead of having 1 pair, we have it split already. Okay? So we have 23 and we have 23. Then what will happen, each of those, that is how we're going to go through what's called prophase 2, metaphase 2, pretty much PMAT2, and then we're going to end up having 4 from the 1. And each one is 1 end, 1 end, 1 end, 1 end. All of them are haploid. Okay? Now again, in your textbook, they might have it as 2n to 1n and a 1n to 0.5n. It's enough for me for you to tell me that it is haploid. Okay? Diploid to haploid, and then we stay haploid. All right? Does that kind of make sense? Okay? Yes?
Wait, so you're saying like 2n is diploid, and then 1n would be haploid, and
Yes.
then it would be haploid.
Yes.
Okay.
That would be fine. Because 0.5n is also haploid. All right? Now in spermatogenesis, you start off with the 1, and you end up 1, 2, 3, 4 spermatocytes at the end. In the female, you start off with 1. And then at the first division, this is where things are different. You see how they are equally sized here? In the female, they are not equally sized. One is larger, the other one degrades. That's a difference. Also to note, in the female, and you can put it right next to this in this prophase 2, like right here. In the female, the large one of the 2 is the one that ends up getting ovulated. Okay, so that's really important here. Where is it right now when it's being ovulated? Okay, so what's happening in that Graafian follicle in the female? This is happening in the Graafian follicle. This is what's happening to the oocyte that is in that Graafian follicle. We're going through these steps, through these steps. And right before that oocyte is meant to be ovulated, it has to perform that first division. Okay? So what happens in the second division? That oocyte, when it gets ovulated, if it does not get fertilized, it doesn't even complete the second division. That's what it means by it being arrested. This is the step right here, arrested. And the second division is not even guaranteed. When does the second division happen in the female, in the oocyte? Only if it is fertilized. Only at fertilization is it going to undergo that second division. Everybody got that? In your homework packet, there is a section in there right when it's asking for this, okay? All right. That's your preview. What's going to be different? Primary sex organs and gonads. I don't have to spend too much time on this one, okay? Because this is all from our anatomy and lab, right? Okay, male reproductive section system. The gonads, of course, are the testes. They are located in the scrotum. The function of the scrotum, by the way, is for temperature regulation. Temperature regulation is spermatogenesis. Spermatogenesis can ideally happen at a temperature that is lower than body temperature. Body temperature is a little bit too hot, a little too warm. Okay, so we have to ensure that gametogenesis, that spermatogenesis, has to occur outside of the body, which is why the scrotum is there. The scrotum is the skin and the muscle that is surrounding the testis, okay, and being able to regulate the temperature, right? We have the ducts for delivery of those gametes. That includes the epididymis. The epididymis is where that that sperm is going to be stored and where it's going to mature. The ductus deferens or the vas deferens, I will take ductus or vas, that's fine if you remember vas deferens, use vas deferens. Ejaculatory duct I talk about, and of course the urethra, and then there are some glands that are going to contribute to the semen along the way, right? And external genitalia, the only one we talked about in lab was the penis and the different parts of the penis. So just to give you a little more detail in terms of the anatomy, okay? Each testis is going to be divided into smaller sections called lobules, about 250 to 300, don't memorize that number. It's a lot of little sections, right? And so histologically, this one you absolutely should know histologically how to recognize that. Each of those little sections are going to contain about 1 to 4 coiled seminiferous tubules. So this is the cross section that we see, but in reality, it is a very highly coiled tubular structure. And so these are where we're going to produce that sperm. We'll talk a little bit about the scrotum. The scrotum is for temperature regulation. It is made up of skin, but also these two sets of muscles are associated with that scrotum. You have the dartos muscle, which is smooth muscle, and the cremaster muscle, which is skeletal muscle, and both of them are reflexively going to respond to temperature changes. So that on a really cold day, then the testes are going to be brought closer to the body. And when it's a really warm day, then the testes is going to be pulled away, or it's going to be more relaxed away from the body, right? And this is all for that temperature regulation that is most ideal for spermatogenesis. This is where I will slow down just a little bit. Okay. The rest of it before was just the anatomy, which I want you to just go over, okay? The gametogenesis part. All right. Review your interstitial cells. The interstitial cells are not part of the tubule. They are not. They exist outside of the tubule and they secrete testosterone. Okay. Got it. That's more of the endocrine part. We're going to focus on this. The sustentacular cells are the ones that will respond to FSH. Sustentacular cells are also known as Sertoli cells, and they are also known as nurse cells. Nurse as in nurturing, as in RN nurse cells. So they go by 3 names: sustentacular cells, Sertoli cells, or nurse cells. The nurse cells, sustentacular cells, is the giant yellow cell that is here. That is the sustentacular cell. The job of the sustentacular cell is not to make testosterone. Its job is to make gametes, which is why you have your spermatocytes in various stages. These are the youngest ones, and they're going to move this way as they develop. So just to give you an idea of where we are, the lumen is it up here or is it down here? Where's the lumen? Where's the inside of that seminiferous tubule? Is it the one at the bottom or is it the one up here?
Yeah.
It's down here. This is the lumen, which you would have noticed that there were tails in that lumen. Okay? So don't forget, while you're here, don't forget what structure secretes LH and FSH. What is the structure? What is the gland that secretes FSH and LH? Anterior pituitary. Remember my flat pig, right? Flat, FL, don't forget that one, all right? So let's look at spermatogenesis. This is pretty straightforward. Should be straightforward. Just highlighting the difference between mitosis and meiosis, and just to let you know that these gametes still have to go several rounds of mitosis first before they do the meiosis. Before they perform meiosis, you start off with the one, and then we do that first meiotic division. We end up with 2, and we are already haploid at this point. And then we perform a second meiotic division, and we end up with 4 from the 1. Pretty straightforward. Let's compare where it's going on. Okay, I'll show you next. So how does this happen? Where does it happen? This process of spermatogenesis is going to start at puberty, and it's going to continue on until death. So continually, again, very different from oogenesis. In oogenesis, This is not continual throughout life. The oocytes, we are born, females are born with all the oocytes that they need. They do not produce anymore. They don't, okay? So for the males, begins at puberty and ends at death. About 300 million sperm per day is produced. So if you think about it, 300,000 per minute. And in an ejaculate, 50 to 120 million ejaculated. And how many sperm does it take to fertilize an ovum, everybody? Out of those, just one. Just one. Just one. So let's trace this. This I would like you to know. And this corresponds to being more outside of the seminiferous tubule, facing the outside toward the lumen, okay? They will start off on the edge and they will make their way toward the lumen. Right, start with the spermatogonium. Spermatogonium is still diploid. Like I said, it's gotta go through several rounds of mitosis first before it performs meiosis. So diploid, we're still at diploid, 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 diploid. Okay, meiosis 1 is completed. That's super important. Once meiosis 1, the first division is completed, it takes on a different name, and that name is going to be the secondary spermatocyte. So we start off as spermatogonium. That is 2N, that is still diploid. The primary spermatocyte, that is still diploid. So 2N, 2N. Secondary spermatocyte, in between, first division. We are now haploid. Second division takes us from secondary spermatocyte to becoming spermatids. If you think of it, spermatids sounds like spermakids. They're still immature, right? They're still immature, but now we've got 4 of them officially. So when is the first division? Between what and what? The first meiotic division between primary and secondary. When is the second division?
Secondary to sperm.
From secondary to spermatids. So let's hear where we are. Hey, there we are. These are secondary spermatocytes. There's the second division. Early spermatids, late spermatids. You don't need to know early and late. Just know there's one group. Those are the spermatids. The late spermatids, this is when they haven't gotten their tail officially yet. Okay? Once they become spermatozoa, they have their tail. Are they fully mature yet though?
No.
No. Where do they need to make a pit stop and kind of stay for a little while? What's after the seminiferous tubules, everybody? The epididymis. It's got to hang out in the epididymis first. And so the epididymis, this is the one that's kind of comma-shaped. Okay, you would have been able to see it, and then those are my Tuesday, you are going to see it today in lab. Okay, it's got a head, a body, and a tail. All right, what is the type of epithelium that lines it? Okay, this actually has pseudostratified columnar epithelium. This is one of the rare places where we find it, apart from this. What's the other place, the more common place to find pseudostratified columnar epithelium? The trachea. That's probably a more notable place to find it. This is kind of a secondary, okay? And it also has a little bit of smooth muscle because we do have to propel that sperm, right? In about 20 days or so, those spermatocytes will gain something called motility. In order for sperm to be fully motile and fully mature, they need to be able to do 2 things. They need to be able to swim real far and fast, and they need to be able to fertilize an egg. That, by definition, is what makes them motile and fully mature. While they're doing that, though, while they're hanging out in the epididymis, they can be stored there for months. And so what is the function of the epididymis again, everybody? If you could put it in one line. Storage and maturation of the sperm. Does it make sperm?
No.
No, it does not. What is the structure that makes sperm? Seminiferous tubules, or just generally the testis itself, okay? The testis itself is not the epididymis. That's completely different, all right? Now we're going to be delivering that sperm, right? We're gonna go through the vas deferens. It stores and transports that sperm away from that epididymis. This is gonna form a major part of what's called the spermatic cord. Is spermatic cord and vas deferens the same thing, everybody? Okay, Tuesday, you might not be able to answer that just yet, But my Thursday, tell me, is it the same thing?
No,
No, why not?
they just wrap around each other.
Not necessarily they wrap around each other, one is part of the other. One is part of the other. What's the name of the whole thing? Is it the vas deferens or the spermatic cord? Spermatic cord. The spermatic cord contains the vas deferens. So it goes through the spermatic cord, right? It's in the spermatic cord, enters the abdominal cavity through this passageway called the inguinal canal. And once we're in the abdominal cavity, then all of the parts of that spermatic cord are going to be separated from each other. And then the vas deferens just continues on into the abdominal cavity by itself. So we're gonna follow that, and then it's going to lead us into what's called the ejaculatory duct. So just to kind of show you where we are, the ejaculatory duct is kind of coming from the back. So to let you know where the vas deferens is, this is the testis, this is the epididymis. The vas deferens has to go behind the bladder. So this is actually the posterior aspect of the bladder. We're looking at the back of the bladder. And so we've got the vas deferens here. It's going to kind of end up in this wider area and then make it into the ejaculatory duct. And then from there, it's going to go through the urethra. And so with the urethra, this can carry sperm or urine, but not at the same time. 3 parts of the urethra. This one was more for lab. There's a part that goes through the prostate. There's a part that goes through this flat area called the urogenital diaphragm. There's a sheet that is right there. And so there's a little bit of that that's going to constitute the membranous urethra. And then you have the spongy or the penile urethra. So the first part goes through the prostate, then there's a part that goes through a membrane, and then there's a part that goes through the spongy part, the penis, okay? Along the way, we're going to add to the sperm. Why do we need to have accessory glands? By the way, in the female, there are no accessory glands, I want you to know. This is solely just for the male. So, the accessory glands along the way. Again, what is the name of this structure? This is the vas deferens. Why is it not the spermatic cord anymore? Where is the spermatic cord? I want to hear from this side of the room. Where is the spermatic cord? Is the spermatic cord inside the abdominal cavity, or does it exist outside of the abdominal cavity? Outside of the abdominal cavity. Once we go through that inguinal canal, all of the structures of that spermatic cord are going to separate from each other. So that means, what does it mean by separate? This is what we're sharing the spermatic cord with. So you have the vas deferens, of course. The gonadal artery and the gonadal vein have to be going with it. And some nerves have to be running with it. That's what makes up the spermatic cord as a group. You've got the vessels, you have the nerves, in addition to the vas deferens. Once it goes through, that whole thing is the spermatic cord. Once we get through the inguinal canal, the vessels will go their own way, the nerves will go their own way, and the vas deferens will go its own way. So that's why it is no longer the spermatic cord when we're in the abdominal cavity. Okay, got it? All right. So this happens to be the vas deferens. So we're going to follow the sperm going through that vas deferens. It's going to end up in this sort of widened part of that vas deferens. And then this is where we encounter the first accessory gland. The first accessory gland is the seminal gland or the seminal vesicle. By the way, all 3 of these accessory glands are going to contribute to a fluid that is going to nourish the sperm. And that fluid is called semen. So that's different from sperm. Sperm are the actual gametes themselves. The semen is the fluid that is produced by the glands in order to nourish the sperm so that it can become fully motile. And so we have 3 contributions to that fluid. Right? All we have here right now is just the sperm. But first, the seminal glands, they are going to contribute 60% of the semen volume. What is in that 60%? You need some fuel, fructose, prostaglandins, and certain enzymes. You don't need to know the names of the enzymes. But that is going to contribute to 60% of that semen volume. Again, is sperm and semen the same thing? No. Okay, which ones are the actual gametes? Is it the semen or is it the sperm? The sperm are the gametes. Okay, then you've got the prostate gland. I'm going to show you where the prostate gland is. This is the prostate gland. The prostate gland is going to contribute to about 1/4 of that volume of semen. This is going to produce something that will enhance the motility of that sperm. That sperm has a long way to go in order to be able to fertilize that ova. And so we have to make sure that it goes all the way, all right? This is also what's going to liquefy what's called the ejaculate. The ejaculate is what is going to be expelled from the body in terms of sperm and the semen together. Okay, that's what's called the ejaculate. And so what will happen is that it's going to liquefy the ejaculate and then it's going to solidify it a little bit. So it's going to change a few, change the consistency of it, but you don't need to know in how much detail, right? You should know that it contributes about 25 to 30% of that. And then there's the smallest amount. This is what's called the contribution from the bulbourethral glands. And so find the bulbourethral gland. First off, where are we? This is the seminal gland. This is the prostate gland. And right about at the base of the penis is where we find a very small gland. That is what's called the bulbourethral gland. The bulbourethral gland prepares the urethra for the semen and sperm to go through. And so the mucus will help lubricate the urethra, but also neutralize the urethra. What is the other fluid that can go through the urethra, folks?
Urine.
Urine. What can you tell me about the pH of urine? It is slightly acidic. Is that good for the sperm? No, it's not. Okay, we want to try to neutralize that. And so that's what the bulbourethral glands are going to do. So, folks, again, what are the 3 accessory glands in order? Seminal glands, the prostate, and the bulbourethral. Excellent. I love how you guys are awake. I love it. You're like, I think I'm awake. Okay, cool. Finally, we've got the penis, external genitalia. This is more for lab, okay? Function delivers the sperm to the female reproductive tract. This part, you don't need to know for lab, but I'm gonna go over here for lecture. Okay, the penis is made up of erectile tissue. So in other words, it doesn't quite classify under any of the 4. It's really a combination of different tissue types. We're just gonna give it a general name. We're gonna call it erectile tissue. Think of it as having a lot of sinuses in it that get filled with blood, okay? And that erectile tissue is arranged in 3 columns that are running parallel to each other. 3 columns. And if we were to do a cross-section of that, that's what I mean. There are 3 columns right there. One of the 3 has the urethra running through it, and the other 2 have some major blood vessels running through it. So let's look at what they are. So this is the single one. The corpus spongiosum is the one that is gonna have the urethra through it. And then there are 2 corpora cavernosa. That's the one that's paired. All right. This is going to make up about 2/3, the bulk of the penis, and this is the main contributor to erection because of the major blood vessels that are in those 2 columns. Okay, so this one, most important thing, this has the urethra running through it. This pair has major blood vessels running through it. Between the 2, what's going to contribute to an erection more? The one that's the paired, which kind of makes sense because it's taking up 2/3. And that's the penis. Always have your concept checks. Be able to outline the stages of spermatogenesis. And there are 2 meiotic divisions that we have to keep track of. So just as a review, when we go from a primary to a secondary anything, that is always the first meiotic division. It's going to be true for the sperm, and it's going to be true for the oocyte. To go from primary to secondary is the first meiotic division. The second meiotic division, if it happens, is after the secondary whatever. Okay? I would ordinarily give you a break, however, as it is the last lecture, we're gonna go all the way through. Are we okay? But if you need to step out during the lecture and just catch up with somebody, that's totally fine. All right? Got it? Everybody breathe in. Breathe out. We still alive?
Nope.
Okay. Dead people don't speak. Okay, yes, Gwen.
So for the, you said from the primary to secondary is the first meiotic division, and then the secondary to something else?
Yes.
So
I'm gonna
we-
say something else
Yeah.
right now.
But question with that, so the secondary is part of both?
Yes,
Oh.
so there's gonna be a primary and secondary spermatocyte, right?
Yeah.
There's also a primary and secondary oocyte.
Okay.
But after the secondary for the sperm, we started calling it a spermatid. In the female, we don't call it an ootid, we call it something else. That's why I say that's something else, because that's where the pattern, the naming pattern kind of breaks. Okay, so from primary to secondary spermatocyte, that's the first meiotic division. From primary to secondary oocyte, that is the first meiotic division also. Yes,
So would primary be like your diploid and then secondary
Yes.
haploid?
absolutely. Primary is always diploid. Primary is always diploid. Secondary is when it becomes haploid. Excellent question, okay? All right, let's look at the female then. With the female, this one we covered in lab. This kind of gives you an idea of what the functions are, right, in general of the reproductive system in the female. Okay, not only is gametogenesis going to be involved here, but also we have the structures that are going to support a developing embryo. Okay, that's a main difference, all right? It's one of the main differences in terms of the function. There are going to be cyclic changes according to what is called the menstrual cycle. The menstrual cycle is going to commence at around puberty. And that menstrual cycle is going to repeat every 28 to 30 days. 28 to 30 days, average 28, all right? This is a monthly cycle as it affects all female reproductive organs. This will be a combination of two cycles that will be in sync with each other. Ovarian cycle and uterine cycle. What do we mean by having two separate cycles? This is what the focus is on with the ovarian cycle. We're gonna watch the follicle. That follicle is gonna become a Graafian follicle. And within that follicle, we have the oocyte, okay? That's what's going on in the ovarian cycle. We're watching that cycle. The uterine cycle does not have follicles. It does not have an oocyte. It doesn't have a corpus luteum and all of that. The uterine cycle reflects the changes in the uterine wall. Okay, so that's a different thing. Why do we need to change the uterine wall? In preparation for possible fertilization. Okay, so the inside of the uterine wall, which is called the endometrium, is going to start to thicken, 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 and then it's going to be shed. Then it's going to thicken, 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 and then it's going to be shed. That is going to be in line with what's going on all the way up in the ovary. So that, as a combination, is going to be your menstrual cycle together. Right? This one is more for your lab. Is the follicle the same as the oocyte, everybody? No. Why are they different? Why can't we use those terms simultaneous with each other? How would you describe the relationship of the oocyte and the follicle?
It comes from the follicle.
It comes from the follicle. The follicle contains the oocyte. Completely different. Completely different. So if I point out to a follicle on the practical, I'm asking for the follicle. I'm not asking for the oocyte unless the pointer is directly on the oocyte. All right? review what steroid hormones are secreted by the ovary. That would be estrogen and progesterone. Okay, what is the Graafian follicle? The Graafian follicle is the largest version of the follicle. That is the one that is going to house that oocyte. And within that follicle is when that primary oocyte becomes a secondary oocyte. So what is the identity of this one that is released? Primary or secondary oocyte? This is the secondary oocyte, which means the first meiotic division would have had to happen somewhere between this step and this step. The first meiotic division has to have happened inside that follicle from about here to here. You won't be able to tell histologically of, oh, is this one the primary or is this one the secondary? It will look the same. Why? Remember what I said, when it divides very unevenly. That first division, you've got something really big, which will become the secondary oocyte, and then you will have something that will degrade, and that's called the polar body. Very, very uneven. So let's follow our gametogenesis. This time, we call it oogenesis. The gametogenesis before was called what in the male? Spermatogenesis, making sperm. Now we're gonna make oocytes. Oogenesis. A little tough to say because you have both of the vowels together. Everybody say it with me. Oogenesis. 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 Okay, if you want to think about it, oogenesis. That's how you're going to spell out oocyte, right? Okay, we're gonna start off with some stem cells. Instead of spermatogonia, we have oogonia instead. Now tell me, what do you think? Diploid or haploid? Diploid. We always start as diploid, right? We always start as diploid. Okay, the primary oocyte. Diploid or haploid? Primary is always diploid. Okay, cool. However, this is what makes it special. It's about to go into meiosis 1 and it gets stuck there. Is it still diploid? It is. Because it may never complete that first division. It's stuck. How long is it stuck there? 13 years, 25 years, 45 years, 50 years. Arrested. So, okay, right? If fertilization happens at age 55, this was an oocyte that's been there for 55 years. Isn't that wild? Why is it then that there is a greater risk for genetic abnormalities? Now you know why. That oocyte, unlike in males, this is not continuous. That oocyte would have had to be there for 55 years just waiting to be ovulated. Okay? So we can be stuck in here for a very long time. Okay? So arrested early in meiosis 1, it will complete meiosis 1 at ovulation, or maybe just right before ovulation, right before it's about to be released. And when it's released as a secondary oocyte. This one is a second arrested. It is arrested in meiosis 2 until fertilization, if it even happens. So secondary oocyte, haploid or diploid? It's officially haploid, but is it going to finish the second meiotic division?
Possibly not.
Possibly not. Possibly not. Okay? When we call it officially an ovum, technically, ovum is referring to the mature oocyte that has completed the second meiotic division, which means that this is the oocyte that has been fertilized. The ovum. Okay? Every time we divide, both times we divide, it is uneven. I've mentioned that several times already. It's uneven. You have one that's much larger, and you have one that will degrade. Every single one that will degrade is what's called a polar body. Polar bodies will degenerate without ever being fertilized. Okay, and this whole process will take about 55, 60 years. Well, not 60, probably 55, whenever menopause is. Okay, takes many years to complete. So, let me me ask you, based on what we know. You get 1 spermatogonium, and you get 4 spermatocytes. How many polar bodies do you get in the female, assuming that fertilization happened and goes through the whole thing? How many polar bodies do you end up with? 1, 3, 2, technically, how many? You're supposed to end up with 4, right? Of those 4, which one actually is the surviving oocyte? How many surviving oocytes do you get from that? Just 1. So really, how many polar bodies did you have to generate in order to get to that? 3. Because you have a total of 3.
Yeah.
So this is what's going on. First meiotic division.
Oh, no.
Okay, this is what? That's the primary oocyte. What's this one?
Secondary.
Mm-hmm.
Um,
If this gets fertilized, okay, what do we end up having? There you go. Okay, this would have degraded a long time ago, but if it were, let's say, just so we keep our numbers kind of consistent, it would have divided like that. 1, 2, 3 polar bodies. And then you have the one that wins. Polar bodies are the little pieces that are discarded. Yeah, because it's a very uneven division. Right, these would never actually divide, but again, we're just kind of keeping track of the numbers. Okay, because this is degraded before it even does that. All right? So that's what that means. The polar bodies will degenerate without ever being fertilized. These are just the discarded daughter cells. 1, 2, 3, 4 is our total after the 2 divisions, 1 and 2, right? 2 divisions. Meiotic division 1, meiotic division 2. Okay? Remember, the first meiotic division takes us from a primary oocyte that is diploid to a secondary oocyte that is haploid. So now that we have that idea, okay, we now have a modified version of what we saw before, where it's not complete and continuous. So, let's start. This part, there's a part in your homework packet that asks, okay, what is the identity of the egg cell at certain times in a woman's life? Even before birth, the primary oocytes are already there. So these primary oocytes, they have entered meiosis, but they're gonna be stuck in that first division. They may not even complete the first division. That's the primary oocyte. When they are born, they still have primary oocytes and they're stuck. They are stuck. Each month, from puberty to menopause, that primary oocyte is going to be what we call recruited. To be recruited into a follicle. To be recruited into a follicle means that you're going to start to have follicular cells surrounding you. That is what the lucky primary oocytes are going to undergo. And if it doesn't happen, it's going to wait 50-something years for it to happen. Okay? Let's follow what's happening with the follicle at the same time. All right. We're going to go ahead and recruit. Be recruited into a follicle. And this is where we go to the primary follicle and the secondary follicle. I don't want you to memorize these steps. Don't worry so much about that. This is what I want you to pay attention to. What's going on with the oocyte. Most important follicle I want you to keep track of is the Graafian follicle, aka the mature ovarian follicle. That's the same as the Graafian follicle. We're looking for the biggest and the baddest. This will all be under the influence of FSH. And when it comes down to it, what does FSH stand for, everybody? Follicle stimulating hormone. Now, does that make sense? The follicles that are most responsive to FSH, those are the ones that are going to win. Hence, follicle stimulating hormone. Right? So this is the one that was especially responsive to FSH, which is how we got to this stage. Meanwhile, okay, we are going to go from 2N to haploid already. Okay, see what happened here? What do you call this thing? That's a discarded cell. That is the polar body. That's that. This is the same as this. We call that the first polar body. This is now the secondary oocyte. This is going to get stuck again. This is the one that is released at, oh hey, check it out. Released at ovulation. This is the secondary oocyte. Then that secondary oocyte, two fates that could happen to it. Either it never gets fertilized or it does get fertilized, only if it is fertilized. Okay, then it's going to complete the second meiotic division. Right? 1, 2, 3, 4. Just like this. 1, 2, 3, 4. Which one do we pay attention to? Only the ovum. The other ones are discarded. So know the steps and when, right? What is present at birth? What is ovulated at ovulation, right? This is the one that is present at birth, the primary oocyte. The one that is ovulated is the secondary oocyte. The one that is fertilized is the ovum. The last part of this are going to be watching our cycles. Watching the cycles. So you have the ovarian cycle, and what's the other cycle that we're keeping track of? This is events in the ovary. What else are we paying attention to? The events in the uterus. Okay, this one we're watching the follicle in the oocyte. In the uterus, we're watching the lining of the uterus. So let's look at the ovarian cycle, 3 phases. The uterine cycle will also have 3 phases, then we're going to put them together and we're going to go side by side, all right? So first, in the ovarian cycle, let's pay attention to the follicle. This follicle is getting bigger and bigger under the influence of FSH. The first 14 days. How long is the whole cycle, by the way, everybody? 28 days, and so we're going to be watching it, okay? First 14 days, the follicles will grow and develop. And under the influence of LH, those follicles will start to secrete estrogen. If you are wondering, okay, those of you who are familiar with the menstrual cycle, if you're wondering what is going on in the uterus at the same time, you know when they say, what is the first day of your last menstrual cycle? The first day of the period? The first day of the period is the first day of the follicular phase. Okay, so the shedding may sound as if it is very terminal and it's at the end. The shedding is actually at the beginning. So while the uterus is shedding, okay, the follicular phase is already happening in the ovary at the same time. At around day 13, 14, 15, there's something very significant that happens. It's called the LH surge. There's going to be a big spike in LH right before ovulation. Without that spike, ovulation will not happen. Without that spike, ovulation will not happen. So the LH surge, you're going to see it all drawn out, by the way. After that surge, one oocyte exits the follicle into the uterine tube. Notice where it ends up. It ends up in the uterine tube. It doesn't go straight into the uterus. When does it go to the uterus? It's only if it's fertilized. It waits in the fallopian tube. And what kind of an oocyte is that one? Primary or secondary? Let's try to review this. Is that the primary oocyte that left, or is it the secondary oocyte that left?
Primary.
It's always the secondary. Always the secondary. Haploid or diploid?
Haploid.
Haploid. It should be haploid. Can you imagine if it were diploid? Imagine what would happen if that were diploid and it was waiting in the uterine tube and then a haploid sperm comes in. How many copies are going to end up with? 3. We don't want 3. We want 2. So this secondary oocyte has to be haploid. Okay, it's going to wait. doesn't degrade. It becomes something else. It becomes what's called the corpus luteum. So this last part, so I would say day 15 to about 28, approximately, we're gonna call that the luteal phase. The luteal phase. What should the uterus be doing at this time? Assuming that this oocyte is waiting, and it's waiting for possible fertilization, what does the uterus have to prepare for?
Create a
If it were creating a lining, if fertilization were to happen, if an embryo were to develop. So that's what the uterus is gonna be doing during this luteal phase. So we got the corpus luteum, this is the part of the follicle left in the ovary. This will secrete estrogens and, most importantly, progesterones. And so I underline that so you remember progestation. This progesterone is going to cause the thickness of that uterine wall to get thicker and thicker and thicker. Okay? All right. So let's look at that in pictures. We like pictures. This was the corpus luteum I wanted everybody to look for. I think you found it. Did you find it?
Yeah,
You
but
did.
it looked a little flat.
It looked a little flat, okay? This is the one ideally we want to find, but if we don't find one like this, if I ask for a corpus, if I want a corpus luteum, I'm likely gonna give you a picture for it, okay? Because picture-wise, this is what that's supposed to look like. This is supposed to be the corpus luteum. Does the corpus luteum have an oocyte in it, everybody? Yes or no? Corpus luteum houses an oocyte, true or false? False. Very false.
It's post already.
It's already after ovulation, so it lost the oocyte already. This is what is left over. So those granulosa cells and the theca cells that used to be there, they become this, because they were left behind. Only the oocyte is going to be ovulated, right? This one, okay, is more for lab, also known as the fallopian tubes. The uterus, this is also for lab. We're gonna fill in some blanks here that we might know. The uterus is where the fertilized ovum ideally should travel, okay? This is where we're going to support that embryo, because there's a lining that is there. The cervix is at the entrance to that uterus. It keeps the uterus closed. This leads to the vagina. Uterine wall is made of 3 layers. What tissue is the myometrium made out of? Smooth muscle. Smooth muscle. The visceral peritoneum, by the way, I refer to it as something different. That is the same as the perimetrium. That's the visceral peritoneum. That's the perimetrium. That was the one that was immediately surrounding the outside of that uterus. The myometrium is gonna make up the bulk of the wall. It's mainly muscular. And this is made up of smooth muscle. Can you name me one hormone whose target is the myometrium? Can you name me one hormone whose target? Progesterone is not for the myometrium, that's for the endometrium. Okay, name me something from the posterior pituitary that targets that myometrium. Starts with an O.
Oxytocin?
Oxytocin. What is one of the functions of oxytocin? There's 2 functions I want you to know. One is for milk release, but what was the second function of that oxytocin?
Uterine contraction.
Uterine contraction. Who's the best one to contract? It's gotta be the smooth muscle. The endometrium does not contract, right? The endometrium is not muscle, right? The endometrium is not an effector. Myometrium is your smooth muscle effector, so that's gonna be the target of your oxytocin, right here. Then you've got the endometrium. The endometrium is simple columnar epithelium. This endometrium is actually going to be in 2 sublayers. 2 sublayers, okay? So I'm gonna show you where the endometrium is. The endometrium is right here. This is the myometrium. That endometrium is actually broken up into 2 sublayers. There's the functional layer and there's the basal layer. The functional layer is the one that gets thicker and thicker and is shed and needs to be replaced. How do we replace it? That's why we have a basal layer of the endometrium. So with every shedding of that of that endometrial wall, the whole thing is not being removed. Only just the functional layer, or else we would never be able to replace it if the whole thing was removed, right? So that basal layer will always stay in place, okay? And the functional one is going to keep growing. So that takes us finally to our uterine cycle. This is now with a focus on the endometrium, the thickening of the endometrium and the release and the shedding of the endometrium. And this is all cyclic. This will coordinate with the events in the ovary, with the follicle, with the corpus luteum. These phases are also going to be directed by FSH and LH. These are the three phases of the uterine cycle. Now we're going to follow the thickness of the functional endometrium. Okay. This represents the relative thickness of the endometrium throughout the cycle. This, if you notice, we go from day 1 to 28, like what we did with the ovary. Okay? The first phase, about days 1 through 5, days 1 through 7, approximately. This is the shedding. So we started out pretty thick over here, and then now it's getting thinner and thinner because that is the shedding. This is the menstrual phase. What is going on in the ovary at the same time? What phase is happening in the ovary at the same time? Starts with an F.
Follicular.
Follicular phase. So we're already starting to develop another follicle, right? We're trying to get it to being that Graafian follicle. At the same time, we're shedding that. Okay, so that's about 1 to 5 days. Then after that, right before ovulation, this is what's called the proliferative phase. Notice what happens. That's from here to here. The proliferative phase, this is the rebuilding of that functional endometrium. Then the secretory phase is for the remainder of that. Okay, what happens between 14 and 15 that's very important? Ovulation. And what surge of what hormone has to happen right before ovulation?
LH.
The LH surge. Okay, good. So we've got the secretory phase as the last part. The secretory phase is days 15 to 28. This is going to prepare the uterine wall for possible implantation. Because at this point, where is the secondary oocyte hanging out? Where is it? Is it in the uterus? Is it the uterine tube? Is it still in the ovary? Where is it? It's in the fallopian tube at around this time. So the secretory phase, this is how we get from this to that. And it gets thicker and thicker and more proliferative with the blood vessels, right? This is what we call the secretory phase, very thick, preparing for possible implantation. And so we put all of those events together. Let's focus on the events around ovulation especially. Okay? This is what's happening in the uterus. This is what's happening in the ovary. These are the hormones that are secreted by the ovary. These are the hormones that are secreted by the anterior pituitary to direct this. So rather than memorizing, okay, at which time is this hormone proliferative or not, there are certain ones I want you to pick out from this, okay? Summary. What is that blue spike called? The what? The LH? Surge. What is this red dotted line represent? What does the red dotted line represent? That is what?
It's what's happening at the same time.
At the same time, but what is this very important event that this corresponds to? Ovulation. So, this is what we can kind of notice. Don't worry so much about FSH. LH we're going to pay attention to. Notice the spike happens right before the red line. Let's look at the steroid hormones. What hormone of the two is especially important past the red line? Progesterone. What is the name of the structure that secretes the progesterone? Who makes the progesterone?
Corpus,
It's the ovary, but what structure? Which one?
corpus
The corpus luteum.
luteum.
Okay, see where you have the corpus luteum here, and then all of a sudden there's a spike in progesterone? Okay? And then look what's happening in the uterus after that. It really starts to thicken after that. So as an aside, I don't have much left in here. This is more for, not lab, okay, and then I'm going to talk to you a little bit about something you may be familiar with that has to do with this. Okay? The last structures here that are the accessory organs would be the vagina and the vulva. The vagina I want you to know for lab. The vulva not so much, but the vagina yes. Okay? Kind of at the entrance to that vagina, we have what is called the vestibule. The vestibule is what's going to house the external openings of the urethra and the vagina. But this one I want you to know for lab. Which one is anterior and which one is posterior? The urethra or the vagina? Which is anterior and which is posterior?
Posterior.
What comes anteriorly? Is it the urethra first or is it the vagina first?
Urethra.
The urethra comes first. On the final exam, on the practical, you're likely going to get that mid-sagittal cut, and it's easy to get them confused. The urethra, the urinary system has to go in front of the reproductive system. So urethra, and so both of those openings are housed in an area called the vestibule. There's the labia minora and the labia majora. These, okay, are the following. What's enclosing the vestibule is the labia minora. Labia means lips. These are the smaller ones, and this is the larger ones. The labia majora is the female homologue to the scrotum. So what it means by female homologue, in development of the female and the male, the default pathway is actually the female. If it weren't for the Y chromosome, then that embryo would have developed into a female, okay? So when we have a lot of what are called homologs, so that means that if it went one way, it would have been this. If it went the other way, it would have been this. The default is for the labia majora to form. If there was a Y chromosome, what would have become that would have become the scrotum, okay? Glans clitoris is the last structure that's here. This is homologous to the glans penis. And so again, it's made by homologous, is that female glans clitoris, this is the default, and the glans penis would have been the other direction if the Y chromosome was there, right? So that kind of finishes up female reproductive, but I do want to mention just one tiny thing with this. I want you to think about the concept of negative feedback. Progesterone, 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 progesterone. What hormone from the anterior pituitary is going to be directing this? First off, this is produced by what's called the corpus luteum. What hormone sounds like corpus luteum to you? Luteinizing hormone. Luteinizing hormone. Okay. So luteinizing hormone stimulates the corpus luteum to secrete progesterone. Okay? The progesterone is going to thicken the uterine wall. Eventually, there's going to be negative feedback that will have to happen, where all of a sudden, that corpus luteum, okay, can no longer produce the progesterone. Why? Eventually, the anterior pituitary, look what happens to the LH. It's going down. If you don't have LH, you don't get a corpus luteum anymore. If you don't get a corpus luteum, you don't have progesterone anymore. If you don't have any more progesterone, you don't get a uterine lining anymore, okay? How many of you have heard of the pregnancy hormone? Or know how a pregnancy test works? Kinda, sorta?
Yeah.
Maybe? Okay. Well, in a pregnancy test, they're looking for something called HCG? HCG stands for human chorionic gonadotropin. Okay, the human chorionic part only tells you that this is a result of the embryo starting to develop. In other words, HCG is something that a woman does not make readily. This is something from the embryo. Okay? The G part is really important though. We were introduced to two gonadotropins already. FSH is a gonadotropin. LH is a gonadotropin. And if we did not have HCG, what did we just talk about? The corpus luteum is going to degenerate. It's not going to be able to make progesterone. And when it doesn't make progesterone, it is not going to be able to maintain this lining. Think about what happens in pregnancy. Why this is a marker for pregnancy. Human chorionic gonadotropin. What hormone is that supposed to be a substitute for?
Progesterone.
LH. So now that there's no more LH, if the embryo starts to produce HCG, HCG can maintain the corpus luteum, which is going to maintain the progesterone, and voila, the lining is going to be maintained. So when somebody is having trouble with their hormone levels, okay, what they could be prescribed early in pregnancy is extra progesterone. Because why? That maintains the lining. Right? So HCG is what we call a homologue for LH. Pretty cool? Okay, now we know. All right, that's it for our lecture, guys. Wow, we're done. Almost done. If you're in Tuesday, we gotta finish period, okay?
You said there was a homologue for.
LH. It's a substitute for LH.